All right, welcome to today's video on what's called rotational kinetic energy. All right, so this is going to be a new concept for you guys. Your learning targets are posted down here. So by the end of this video, you should be able to calculate what is called the rotational inertia of different objects. That's a new term, okay? So we'll learn about rotational inertia. You should understand how that rotational inertia affects the motion of objects in different circumstances. You ought to be able to solve simple problems dealing with the point of this video, which is what's called rotational kinetic energy. Okay, you should understand that a rolling object has both kinetic energy and rotational kinetic energy, and we'll learn how to write the total kinetic energy, which is the sum of kinetic and rotational kinetic energy, in terms of the kinetic energy. And then finally, you ought to be able to solve conservation of energy problems. All right, this last one is really kind of the big deal. All right, so conservation of energy. So what you need to do is think about the important points in the object's motion. And for these problems, we're going to learn that there are no non-conservative forces doing work, and therefore our total energy will remain constant. Okay? So here we go. All right? So first of all, when we did our chapter on energy, we learned that a moving object has kinetic energy. Right? And that the kinetic energy depended on the velocity of the object and the mass, right, in this equation. All right? So it turns out that similarly, if you've got an object that's spinning, that spinning object has what's called rotational kinetic energy. Okay? So that should sort of hopefully make some intuitive sense, right? Like if I spin this wheel, all right, it's not technically moving, so it doesn't have kinetic energy, but the individual particles of the wheel have mass and they have velocity, so they have the individual particles have, kinetic energy, right? So what we do is we sum those kinetic energies together to result in what's called rotational kinetic energy. Okay? So this wheel, we would say, has rotational kinetic energy. All right? And that rotational kinetic energy depends on what's the angular velocity, in other words, how quickly it's spinning. Okay? And it also depends on what's called rotational inertia. All right? We're going to use the capital letter I to represent rotational inertia. Often, textbooks, instead of using the term rotational inertia, they use the term moment of inertia. It seems like that's getting less common. I think most people tend to prefer this term rotational inertia. But when you get to college, you might have an older professor, and they might talk about moment of inertia. Okay? So we need to talk about how to calculate moment of inertia. So really, to do this requires some calculus, all right? So basically what's going to happen is I'm going to give you, here, some different shapes and their corresponding rotational inertias, okay? So this is on the back of your equation sheet that I gave you at the beginning of the year. So let me kind of run through these, all right? So the first one there, this guy, a thin rod about its center. So what that represents is something like this, where you've got a thin rod spinning like a baton. Ooh, right? Okay. Now notice it doesn't have to be cylindrical. A meter stick would work just as well. Okay. So this is also a thin rod spinning around its center. Oops. Okay. All right. So the equation for the rotational inertia of a thin rod rotating around its center is 1/3 times the mass of the rod times r squared. And notice what r is. R is sort of the maximum radius from your axis of rotation, okay? So on a meter stick, r here would be half of a meter, right? Because here's my axis of rotation, and I'm, this is the outer edge, so, right? Okay? Now, you may see this depending on the sheet you look at. Sometimes this will be expressed instead of in terms of r, it'll be expressed in terms of the total length, but I don't like that, so I've tweaked them to all be kind of set up the same way. All right, so that's that. Now the second one here, this guy, is same idea. It's still a thin rod, but this time it's pivoted around the end, so it's rotating like this, okay? But it turns out the equation is still the same, right? Okay? The next two are similar, but instead of being thin rods, they're like slabs. Okay? So this third one here would be something like this, or like this. Okay? And this last one, at the bottom down here, this one comes up a ton. the way it's positioned on your screen, it looks kind of like this, right? Okay, so here's my axis of rotation, and it's rotating like that. Okay, that's also a door, right? Okay, or a gate, okay, would be like that. Okay, so all of these objects have, well, actually, I'm getting ahead of this. All right, so let's see, what about the next column? So the next column, so a disk, so that would be this, spinning, you know, about its center. Okay, a hoop, spinning, again, about its center. You probably can't tell that it's spinning. Solid sphere here, so this would be like a bowling ball. I didn't grab a bowling ball. And this bottom one, sorry, bowling ball. And then this bottom one would be a spherical shell. So this one is hollow. So like maybe a basketball would be like that, right? Where all of the mass is concentrated at the outer edge. Okay, so anyway, so there's these different shapes that can be spinning, and these objects have what's called rotational inertia. All right, so in the same way that regular inertia, mass, is sort of a measure of how hard it is to change the linear motion of an object, rotational inertia, all of these guys, represent how hard it is to change the angular motion of an object. Okay? So these will become more relevant once we get to torque. Okay? But for right now, basically you should understand this, and this you probably want to write down. The more rotational inertia an object has, in other words, the larger I is for an object, the harder it is to change the way or the rate at which it's rotating. Okay? So that is that. All right. Now there is another screen of these. All right. So there are some other ones. Honestly, I don't use this page as often. The main reason I included this one is because it's got this guy, which does come up occasionally. All right, so the reason I like this one is that it illustrates the fact that the rotational inertia depends not just on the mass and the radius and the shape, but also the axis of rotation. Okay, so a hoop spinning this way has a rotational inertia of mr squared. Okay, but this one here is showing us that a hoop spinning this way is 1/2 mr squared. Okay? All right, so deriving these requires some calculus. We won't be doing that, all right? Unless you take AP. All right, so finally, sometimes you'll have like a point particle, in other words, a very small object rotating in a circle. So that would be like if I took, you know, some small object and had it spinning around in an object in a circle like this. Okay? So if you wanted to find the rotational inertia of something like that, it's just mr squared, okay? So you might use this if you're talking about, like, if you wanted to find the rotational inertia of the moon as it orbits the Earth, okay? So there you go. All right, so what does all of this have to do with anything? All right, well, let's see what this has to do with conservation of energy, okay? Well, actually, let me pause for a second. Rewind. So once you've got that rotational inertia, once you've calculated that rotational inertia, then we can calculate the rotational kinetic energy of an object. All right, so the rotational kinetic energy of the object is, it's 1/2 I, so the inertia, times the angular velocity squared. Okay, so 1/2 I omega squared. All right, so there we go. So let's use this to solve some problems. All right. So this first example is review. There's no rotational kinetic energy here. It just simply says, what if we slid a box down a frictionless ramp that was 3 meters tall? What would the velocity be at the bottom? So, frictionless ramp. Our height over here is 3 meters. So here's our box. Here it is at the bottom. Okay? So we're interested in the velocity at the bottom, right? So let's see. Height at the top is 3. Velocity at the top is 0. At the bottom, the height is 0. We're looking for the velocity, right? Okay, so hopefully this looks familiar. So what you should be thinking at this point is, okay, well, gravity's pulling this thing down. That's a conservative force. It's not going to change my total energy. There's normal force, but that's not going to do work. So my total energy is constant, all right? So what I know then is that the total energy at the top is equal to the total energy at the bottom. Okay, so problem solving, I want you guys to still be using the same technique where you identify the important points in the motion, and then ask yourself what you know about the energy at those points, all right? And in this case, they're equal, okay? So, at the top, all of our energy is GPE, right? And at the bottom, all of our energy is kinetic energy, all right? Oh, so that means mass times acceleration of gravity times the height at the top is equal to 1/2 mass times the velocity at the bottom squared, right? Oh, okay, cool. And then my masses cancel out. So now I can plug in my numbers. Let's see, G is 9.8. Height at the top is 3. That's got to equal 1/2 the velocity at the bottom squared. Do some algebra and solve, and the velocity at the bottom turns out to be 7.67. Yep. Okay, so that should hopefully be review, right? This is a basic conservation of energy problem. Also worth noting, notice that the length and the angle of the ramp didn't affect that at all, right? Okay. All right, so that's that. Now, what if instead of sliding the box down the ramp, what if we had an object that was rolling down the ramp? Okay, so for our next example, what we're going to do is, instead of having a box sliding down the ramp, we're going to have a disc rolling down the ramp. All right, so we're going to use a solid disc and then the same ramp. All right, and we're going to try to find the velocity at the bottom. Okay, so here's the deal. So let's see, same setup. Okay, here's my disc. All right, so up at the top, I know that the height is 3 meters. I know the velocity is 0, and I know the angular velocity is 0, right? Because it's not moving. Okay, so then I'm going to let it go, and it's going to, roll down the hill, right? And so by the time it gets to the bottom, the height is 0, but now it's going to have both linear velocity and angular velocity, right? Okay, so, my setup is basically going to be the same. I'm going to say, all right, my total energy at the top is equal to my total energy at the bottom. All right, so that means that my gravitational potential energy at the top, because that's all the energy I have at the top, is equal to, now at the bottom, I've got both regular old kinetic energy, because the disk is moving linearly, but it's also rotating, right? Okay, so we got to figure out a way to deal with this. All right, so here's the deal. I'm going to take a quick side note, and we're going to do this. First, a quick and very, very important note about rolling that is going to make this problem much, much easier to solve. Okay, so here we go. All right, so here are some of the different shapes. Here are some of the different shapes that you can have that might be rotating, right? You could have a disc, a hoop, a solid sphere, a hollow sphere, right? So notice all of these objects have a rotational inertia that's some fraction times mr squared, right? So it's always something times mr squared. Notice here our fraction is just the number 1, right? Okay, so this is a thing that I've never seen this in other, I don't know, nobody's ever presented this to me this way, but it's always seemed like a really easy way to deal with these, all right? So what I'm going to do is I'm going to give those fractions a name, all right? Let's call those fractions, I don't know, let's use the letter B, capital letter B, okay? So, in the case of our cylinder here, B is 1/2. In the case of the hoop, B is 1. For a sphere, B is 2/5, and for a hollow sphere, B is 2/3. All right. So for every single one of these, I is B, some fraction B times mr squared, right? Okay. Now, the idea is this: if an object is rolling, and this is huge, this is only true if it's rolling. All right. So remember when we did rolling problems earlier this chapter, one of the things we learned was that the velocity of the object that's rolling is equal to the angular velocity times the radius, right? Okay, or maybe more usefully, our angular velocity is equal to v over r, right? Okay, so check it out. Here's what this buys us. All right, I'm going to clear up some space on the board. All right, so here's our object. It's rolling. So here are the things we know. We know that I is b times mr squared, and we know that omega is v over r, right? I'm going to use capital R there since these are all capital R's. Okay, so check it out. Rotational kinetic energy is 1/2 I times omega squared, right? So I'm just going to substitute in, okay? So we're going to get 1/2 times I times omega squared. Okay? And so what does that give us? It gives us 1/2 B m r squared v squared over r squared. So first of all, notice these guys cancel out, right? Okay, so now I've got this. Oops, I wanted that to be black. You got this 1/2 b times mv squared. Oh, well that's b times 1/2 mv squared, right? Oh, well that's b times whatever the kinetic energy is. Okay? That seems like a useful thing to know. All right? So what that means is, when rolling, our total kinetic energy is the sum of the kinetic energy plus the rotational kinetic energy, right? Okay, well our kinetic energy is 1/2 mv squared. Our rotational kinetic energy we just discovered is b times ke. So this is ke plus b times ke. Okay, so if I put a 1 here, then this is 1 plus b times ke. All right, so this is big. Anytime an object is rolling, the total kinetic energy is 1 plus b, where b is this fraction here, times their kinetic energy. All right, so let's go back to this problem here. All right, what this means then is this is the gravitational potential energy at the top is, now this is just my total kinetic energy, right? So this is just 1 plus b times our kinetic energy, right? All right, so let's plug in our numbers. So let's see, GPE at the top, that's m times g times the height at the top equals 1 plus b times ke is 1/2 m velocity at the bottom squared, right? Okay, so let's see, the m's cancel out. You gotta make sound effects. All right, and then let's, I think I said this a minute ago, let's actually plug in our numbers here. So g is 9.8, height at the top is 3, 1 plus b is 1/2. Right? And now we can solve this, right? So what we did here is, even though we've got rotational kinetic energy, we were able to write an expression for the energy that depended on the velocity, and we didn't need to worry about this angular velocity, right? Because we basically used a jumper equation to rewrite that angular velocity as v over r, and everything canceled out. Okay? So, doing the math here, you get 29.4 equals 1 plus 1/2 is 3/2 times 1/2 times the velocity at b squared, and then go through your algebra, and the velocity turns out to be 6.26 meters per second. Okay? All right, so notice here the velocity is less than it was when we just had the object sliding, right? Okay, and the reason is, when it's sliding, all of the gravitational potential energy gets converted into just regular old kinetic energy. All right, when it's rolling, that kinetic energy is shared, and some of it goes into linear kinetic energy, and some of it goes into rotational kinetic energy. All right, so here's what I'd like you to do. Pause the video real quick. Well, not right now. Okay, so now here's another example. Same exact problem, but this time it's a hoop instead of a disk, right? So we've got a different equation for our I. All right, so take a second, pause the video right now, and see if you can figure out what the velocity is going to be at the bottom of that same ramp. Okay? Okay, so let's do it and see what we get. So the idea then is, once again, you've got your ramp. We know up at the top the height is 0, velocity is 0. No, I'm lying. The height at the top is not 0. The height at the top is 3 meters. Velocity at the top is 0. Angular velocity at the top is 0. And then it rolls down the thing. When it gets down to the bottom, our height is 0, but now we've got linear and angular velocity, right? Okay. So total energy at the top is equal to total energy at the bottom. So that means that we've got gravitational potential energy at the top, and at the bottom we've got kinetic energy, and at the bottom we've got kinetic energy and rotational kinetic energy. Okay, so that means since it's rolling, we can rewrite this mess as 1 plus b times the kinetic energy, right, at the bottom. Okay, so let's see, GP at the top. So that's mg height at the top equals 1 plus b times 1/2 mv squared, v at the bottom. And now we can plug in our numbers. Oh, before we do, m's cancel. All right, let's plug in our numbers. So g is 9.8, height at the top is 3. B here is 1, so 1 plus 1 is 2 times 1/2 times the velocity at the bottom squared. 2 times 1/2 cancels out. Solve it. The velocity at the bottom here turns out to be 5.42 meters per second. All right, and notice it's slower, right? Slower than either of the ones that we did before. And the reason is because our B here is bigger, that means we're going to have more rotational inertia. That means it's harder to change the rotational motion of a hoop, all right? And we'll talk in class about why that is. There's 2 demos that I need to show you in class, and make sure I show you them. I tend to be bad about this. So make sure I show you the hoop versus the disc demo, and make sure I show you the meter stick with the weight at the end demo, okay? All right, because those will both kind of help you better process this, all right? All right, now, through all of this, I neglected to do something that's super important, which is this. These rolling problems, I need to show you, I haven't shown you yet that, that these are, in fact, conservation of energy problems, all right? So it turns out that they are, all right? So when you've got an object rolling, there's actually 1, 2, 3 forces acting on your object, all right? So you're going to have gravity pulling it down, all right? That clearly does work, but it's a conservative force, so it doesn't matter. You've got normal force, which again does work, which does not do work because it's perpendicular to my displacement, right? Okay? Now, here's the deal. So it turns out that if there was no friction, then our disk here would just, it would just slide without rolling, okay? You have to have friction here to make this thing roll, okay? So it turns out there's one other force. There's a little frictional force here that causes the wheel to spin this way, okay? And that's what that force of friction is doing, is it's actually converting basically your gravitational potential energy into rotational kinetic energy. So the weird thing here, though, is technically speaking, it doesn't do work. Because at the point of contact here, the idea is that point doesn't move at all, right? And this is maybe another thing that I need to show you in class. So if you picture like a book tipping over, suppose I've got a book on this thing here, okay? So the idea is if this book tips over, then right here there's no motion, right? Okay, and so your displacement is 0. So when you do work equals force times displacement, your displacement at that point is 0. Okay, so it turns out that friction doesn't actually do any work when you've got an object rolling, which is interesting and weird. Okay, now if the object was sliding at all, then that would definitely change things. Okay, So because of that, these rolling problems are still conservation of energy problems, all right? Probably worth writing that down. If you missed that, rewind it and write it down, all right? The friction does not do work because at the point of contact, where the wheel or hoop or whatever is touching your surface, your displacement is 0, okay? All right, so finally, let's do an example where you've got an object that is not rolling, but just tipping over, okay? So for this example, what we've got is a meter stick, okay, that's, standing on a floor, and then it's going to tip over, okay? Oops, like this, okay? So the idea is this point here is going to stay fixed, okay? So when we did the high jump lab, I talked a little bit about calculating the gravitational potential energy of an object. And so technically here we need to worry about the height, the thickness of the object, okay? So this thing has a center of gravity that is at the center, right? Because a meter stick is uniformly distributed, right? So as it falls, that center of mass is going to fall down through this height, right? Which is half of a meter, right? Okay, so here are the 2 points I care about. So up here at the top, my height is 0.5 meters, right? Because that's the average location of my mass is right here, and right now it averages half a meter above the ground, right? And then at this point, there's no motion, so all of my energy at the top is going to be GPE, right? Then, as it falls, it begins rotating, right? And so at the bottom, there's going to be some angular velocity, all right? Notice I'm not using regular velocity here, right? Because the meter stick's not actually sort of moving. It's not changing locations. It's merely rotating about a fixed axis, right? Okay, so at the bottom, that's my deal. Okay, so this is different from the 2 examples I've done before because it is not rolling. Okay, so I can no longer use that total kinetic energy equals 1 plus b times ke thing. All right, so here's all we're going to do. We're going to go, all right, well, the total energy at the top is equal to the total energy at the bottom. So the GPE at the top is equal to the RKE at the bottom. So let's see, GP at the top is mass times g times height at the top. That's got to equal 1/2 I times omega at the bottom squared. And now we can just plug in our numbers, right? So let's see. Because this is a thin rod, here's our equation for I. So I just got to plug in my numbers, all right? So let's see. Oh, actually, I can't plug in numbers yet. I lied because we don't have the mass, right? So let's see how this mass shakes out. So this is mass times g times the height at the top equals 1/2 times 1/3 m times r squared times the angular velocity at the bottom squared. Okay, so now we can plug in our numbers, but before we do, notice, hooray, the masses cancel out, right? Okay, so let's plug in our numbers and see what we get. We're going to get 9.8 times the height at the top we decided was 0.5. That's got to equal 1/2 times 1/3 times r. Notice r is the total length of the meter stick, which is 1 meter. Don't forget to square it, times omega at the bottom squared. Okay? So, what are we going to get? You get 9.8 times 1/2, which is 4.9, equals omega at the bottom squared over 2 times 3 is 6. And then solve it. And the angular velocity at the bottom turns out to be 5.42. Weird coincidence that that's the same as the last answer, but this time it's radians per second, right? Because it's angular velocity. All right? So, conceptually, still just conservation of energy. You got to deal with this rotational inertia, and then it's just a lot of algebra, really. Okay? So there we go.